Hello, good afternoon, everybody. So this session is we're going to embarking on the road drainage, chapter 3. So we'll be talking about the catchment analysis in the rural area and as well as the urban area. Later on, we're going to design the design for the stormwater pipes. We will be looking at examples to design for stormwater pipes as well as the open channel, and later on we will also looking at the covered design. So actually this one, the covered design will be the project, okay, the 20% project for the covered designs. So after that, we're going to look at the other thing, the for the road drainage, the requirement for the road drainage, and how do we solve the collection, and then the ways how to drain away the water effectively. So this first part, we will be looking at the three main purposes of road drainage. Okay, so the three purposes, as you can see on the screen, firstly is to maintain as far as practical the natural flow of water that exists that prior to the construction of the roads. So look at the this picture here. We're going the covered is allowed the waters, the stream to pass for the natural stream to pass below the road. So this so we can maintain the existing the waterways. Secondly, to collect water, surface water flowing on a road reserve, including the pavement and shoulder, and to channel it to a suitable discharge point. So we're going to look at the within the road reserve. How the water will go through. That's for the, if it's for the within the road reserve, it's quite easy, just a roadside drain for the for table drains. But if you design for the, let's say, the covered crossing or the bridge, which we're going to show you later on, then we need to look at the whole catchment. So we have to look at the whole river system within the watershed, the watershed for that stream, which you're going to put a covered or the bridge. So that one we look at that. Okay. Thirdly, to control groundwater levels and pavement moisture content so that the structural performance of the pavement is not adversely affected. So there are so much components of water that we're going to talk about regarding the pavement. The water from top, from the side, from the bottom. The main aim of the the pavement is to keep it dry for the pavement materials, as well as for the subgrade, which is just at the formation level. That's the the part that we need to compact properly before receiving the pavement material, the sub-base, the base course, and the wearing course. Okay, so we start with the first part, the maintenance of the natural flow of water. So in this first part, we will look at the catchment analysis. We look at the as well as the design of the stormwater pipes and the open channel, and also we're going to look at the covered design. The second part and the third part we're going to look. There will be we look at it separately to later on. So to the maintenance of the natural flow of water, maintain the natural flow of water, various drainage paths. So it could be the rivers, it could be streams, it could be creeks, it could be gullies and watercourse. To do that, we either do the bridge or culverts, okay, that we need to put across to allow the water to flow through. So they need to be sufficient size. Okay. The main thing is that we need to do the capacity design. Make sure that the culvert or the bridge are big. The size are big enough. So if the stream or is quite sizable, then we have to go for a bridge. If it's capacity, the discharge is not that big, we could do with the culvert. It could be a round, it could be a square, it could be a different type of shape. Sometimes there's oval as well. Okay, and then different materials. For the drainage furnitures, whether it's a bridge, whether it's covered, whether it's even the drains, we have to make sure that the velocity is not too high, because the high velocity of flow, it can result in scarring or erosion of the rod. It can wash away if there's a heavy, the discharge is so heavy that it could potentially wash away the whole rods. Even if the flow is let's say is the capacity is not flood, is too high, then it could cause very serious scarring at the outlet of the culverts or the bridge. So for example, you see a lot of if you not protect properly, the river obviously is flowing from this side, the right hand side, to the left, on this picture. So if the water is flowing very fast, it could create a pond at the outlet end. So we need to protect it properly. Sometimes we use the riprap, just a lot of this one, the big boulders or rocks, at the exit end, to make sure that there's the water exiting from the culverts will not erode the outlet. At the extreme event, when there's if we didn't design the capacity properly, either it's a culvert or the bridge, the whole thing, it could be washed away. The whole culvert will be washed away, and even worse, even the part of the rod will be washed away as well. They will be disastrous. There will be failure of rod. It's so actually the rod engineers or the drainage engineer who designed this rod will be called into, they're responsible for this faulty design. It's probably the capacity is not right, it's too small, it's under design. So the first step is to estimate the design flood flow for each of the catchment concerned. Then the hydraulic design of the necessary bridges, culverts, and other drainage structure can proceed. So we need to look at the catchment. This is the catchment of the rivers. This is for example, the point of interest is at this bottom. At the bottom here. We might have a culvert or a bridge crossing. A rod will be running through there, and then we have to put a culvert or a bridge here, so that to allow the water to flow through. And this river system is consisting of so many tributaries. From the upstream, from the furthest point, all the water, we need to consider the areas where you can collect all the waters. So these are usually there's the divider will be at the top of the ridge or the hills, where you can see where the water, it will go to this side of the slope or to the other side of the slope. So this is a divide. We need to find the boundary. These are the boundary usually along the top of the hills, you know. So we need this within the red line. This will be the catchment boundary for the river system that will contribute to the discharge at this point here at the downstream end. These are the upstreams. Okay, there are a few tributaries. For example, this here 1, 2, 3 tributaries. Okay. So we could normally when we look at the design, we wouldn't be given a normally the 3D, but rather we be full of contours. So from the contours, we need to look at this 2D drawings. We need to establish the boundary. So and then within the boundary, then we can find the areas of the boundary, and then we can do some calculation to find the discharge that we need to provide. You know, we need to provide a culvert here or a bridge here, so that will be sufficient. That will be sufficient at the worst event. That means that the highest flood level. You know, so we need to design the whether it's the extreme event. It could be 50 years. It could be once in 50 years, or it could be once in 100 years, depending on the requirement. So to design for the peak discharge, it will be similar. It will be the same formula for whether it's the rural, and we have another one for the urban. This urban peak discharge is same formula as well. Oh, sorry, I think I'm going a bit too fast. I missed something. So this one, I think I just the link to the wrong place. I think. Let me see. Okay. So first, we need to talk about the annual accident probability. In short form, it's AEP. So this AEP is the chance or the probability that a natural hazard can occur, and it's expressed as a percentage. So usually, you know, the bigger rainfall events, you know, got big flood. Normally, it will occur less regular, isn't it? Usually, the smaller flood, you know, then it will occur more regularly. So the bigger event will have a lesser annual probability. So these are the big event, you know. This big event. Usually we measure by AP or the ARI, which means that annual average recurrent interval, ARI. So it could be like some big one. It could be 1 in 50 years or 1 in 100 years. Sometimes even, you know, extreme event. If we design for something bigger, for example, a big dam, we may want to design for 1 in 500 years. So the stream become the rod become the river. So people will do some sport. So jet ski will be on the rod, sailing on the rod. Or some people some children may swim on the rods. So there's in the event of flooding. Okay, so the AEP as annual accident probability. So let's say 2% accident probability rainfall. So that means that it has a 2% chance of occurring in a year. So in a year there are 2% chance of happening. So when it transform to like how many once in how many years, which we call is ARI, annual. I think we mentioned other places. Return years, okay, just return years, which I think we put it somewhere else. So for example, this ARI, they have this ARI as well. So these two are equivalent, ARI or AEP. ARI. They are just one. The AEP is just a percentage, but where ARI is in fraction. So the 2% AEP is equivalent to 2 divided by 100 equal to 1 in 50, or we just say 1 in 50 years. Similarly, 20% AEP, when you do it, become 20% become 20 divided by 100 equal to 1 in 5. That means 20% AEP, it means that the chance will be 1 in 5 years chance of happening. The design storm. All storm systems shall be designed and constructed for an asset life of at least 100 years. That means that the asset, the rods, the culvert, the drain, they need to be designed for 100 years. Okay, ponding on secondary floor on local roads shall be limited to 100 mm maximum height at the central line and velocity such that the carriage rate is possible in a 5% AEP storm. That means that when we design for the some, I think, residential area, the resident, usually whether it's residential and the commercial or industry areas, so we actually not only that we design for the stormwater pipes or the open channel, the table drain, we also allow for secondary system for the water to pass. That means that we allow the water, let's say for a 1 in 20 years event, we allowed the rod to be used as a secondary floor system. Yeah, secondary floor system. In this secondary floor system, we're not going to flood the whole rod, but we allow this one, the water, to be like limit to a maximum of 100 mm maximum height at the center of the rod. So for 100 mm maximum height is still possible for a lot of the traffic, for the cars, So that means that the rods for this secondary floor system, we limit to like 1 in 20, let's say 1 in 20 years event. The road surface can be used second floor, but we limit we design it, the maximum should be not more than 100 mm, so that it still can be used by the traffic. So in this New Zealand the stormwater system NZS 4404, the recommended AEP for the design storm. So surprisingly, actually, the like 20%, so 1 in 5 years, 1 in 10 years. So residential is allowed to flood in once in 5 years. The rural area is allowed to flood once in 5 years, and the commercial is 1 in 10 years. When there's no secondary floor path, certain place that you don't have a rod to be used as secondary floor path, then you have to design for 1 in 100 years. Okay, so other secondary system, the rod, we design, the return period is we design for 1 in 100 years. So it's quite surprising that even we don't design for like the rural areas like 1 in 50 years. Actually, we allow to like flood, to have some flood the water on the rods, once once in 5 years, but the limited is limited to the height of not more than 100 mm. Also, in this time of change in the climates, I think now is the time I think is which is getting warmer. So when it's getting warmer, then the ice the ice sheet at the polar North Pole, South Pole, or the also in the Greenland, I think they starting to get melt, and then they become it will cause the sea level to rise. So so now, like, we have to, in New Zealand, we have to plan out the decision that up for this period. Now it's 2020, so we need to plan out to the time like 2090s. Okay, so 2090s, which is 70 years from now. Okay, so we have, when we do this project, we need to assume use a best sea level rise of 0.5 meter to be used. So that means that now whatever the sea level is, whatever it is, we usually put the sea level, mean sea level, to be zero for the land and surveys, the benchmark land 0. But this 0, the sea will rise from the existing value to 5 meter higher. So that means that your land survey point, it will be all changed. Previously, let's say you have your land survey value, the elevation is 5 meter high land survey, with respect to the sea level. With this sea level rise, your 5 meter, it will become 4.5, because 5 meter minus 0.5 becomes 4.5, because the sea has risen like 0.5 meter. Secondly, B, an assessment of potential consequences from a range of potential highest sea level rise value. At the very least, all assessments should consider as consequence of mean sea level rise of 0.8. Okay, so so therefore, sometimes there's a potential higher sea level, then we need to put a higher value. But I think if you do projects around New Zealand, I think there will be some bylaws. There will guidelines to see how much sea level rise that you need to consider. Okay, for longer planning, then you need to like beyond 2100, that is about 90 years. Then you need to allow 10 mm rise per year. So let's have a look at this sea level rise in Auckland. Let's say if there's it could be many years from now. If there's a 10 meter sea level rise, there's many part of Auckland will be flooded. And you see now, there will be the east coast, it will be navigable from the east to the west. Now this is the the Manukau harbor, and then this is Hauraki Gulf. So actually you can sail a boat through from the east to the west. So actually the northern part will become a separate. You'll be separated from the southern part. So we have another island. And for many years from now, if you have 25 meter rise, more parts, more places will be flooded. Okay, so Yeah, so you can see that what's the impact of the sea level rise. Actually, this one is happening before. I think it's during the last, I think, what is it called? Because they usually the period of glaciation, isn't it? It calls glaciation. So there'll be when the place is very cold, then the sea level. When there's this one is cooling of the planet Earth, then the sea level will be very low. When there's warming, then the sea level it will rise. I think it happened before that, the sea level once. I think there's a cycle many times before the sea level I think has risen to a quite a high level before. So it just it's a cycle of events to be happen. Okay, so the waterway shall be designed for 100 years ARI. Okay, so we look at that. I think this one is just we I think as for the design, I think I have design like covered. We design for like 50 years, 150 years, and bridge also 150 years. For major one could be 100 years. So with that, this 100 years sort of just a guideline. Then if your design, there'll be, I think you have to look at the requirement of from the authorities. The freeboard for the level of serviceability of traffic shall be what is a freeboard? Freeboard is just the there's a space below the soffit of the bridge, and then also there's a gap between the top level of the culvert. There's just there's a gap, that's called a freeboard. So you not the water of the bridge, the water below the bridge will not go up to touch the soffit or the deck, the bottom part of the bridge. So there's a gap here, like in this case of 0.6 or 1.2, and the culvert, you need to leave a gap of 0.5. So for the normal circumstances for the bridge, and this one is some bridge, they may have the big trees coming down from upstream. So this one you have to allow for the like 0.6 for normal, and when there is an extreme event, the bridge have a big trees coming down, passing through the bridge, below the bridge, they need to allow for a bigger gap or bigger, we call it a freeboard 1.2. The culvert, for all situations, the culverts could be like 1.5 meter, 1.5 meter, 1.2 meter, you could be 1.8 meter, or even 2.1 meter height, or usually if it's a round culvert, you have a diameter. So you need to have like 0.5 meter the freeboard to allow for any debris from passing through. Okay, catchment. Catchment is so-called a drainage basin. It's the area of land bound by watersheds draining into a river. I think we have seen this one before. So where is that? Yeah, okay. So the formula for to calculate the peak discharge for rural, and then just now we said it for both rural and urban, the formula for this rational formula by this modified form of rational methods is Q equal to CIA over 360. Q is the peak discharge, and the unit is meter cube per second. C is the dimensionless runoff coefficient. So this one, it depends on all the type of surface, how whether it's a lot of vegetation or whether it's very bad bare, you know, there's no barren, there's no nothing. It's a built up areas. So we look at that, you know, the lowest one will be like 0.1, which is like soil which is cultivated, you know, this the soil been, the ground been tilled, and then for it's completely clear of vegetation. It just to people, the farmers, you put some seed and then to grow some, maybe some vegetables or something or whatever, some fruit tree, usually the vegetables. So this one, you know, is completely, that's without any vegetation. It could be as low as 0.1. So that means that most of the rain falling down on the surface will go to the, you go underground, underground. Okay, so only like 10% will be as a surface water. So when you go it higher, you go to 0.7, you know, and then we have 0.9. These are developed areas. When the area is like fully roof, steel, non-absorbent roof surface, asphalt and concrete paved surface, you know, all the fully built area, the seal surface, and you have the sea become very big, very big. That means that most of the, like in this case, like 90% of the floor will be surface floor, and then like 10% will become the subsurface or the will go underground. So the runoff coefficient will usually is between 0.1 and 0.9. I is the average intensity of rainfall for a duration equal to the time of concentration, Tc. Okay, so for the I, this is the time of concentration of rainfall. So the unit is millimeter per hour. Okay, so for every part of New Zealand we have a rainfall station. So they will calculate the rainfall. You know, they have records of rainfall, and then from the, based on the annual return periods, then we can find out what is the intensity. Okay, so first of all, actually before you find the rainfall, you need to know the time of concentration. Okay, the time of concentration. So this time of concentration is another formula. For example, this one is Tc equal to FL divided by A to power 0.1 divided by S to power 0.2, and then the F. You know, these are all the things mentioned. The unit is quite is a bit unusual. You know, you have the like kilometer square, kilometer, meter per kilometer. So there are, but we are not going to satisfy the dimension. What's that? The compatibility. Okay, so all the dimension you may not be able to get the right dimension, but you have this F here to do it. Okay. So so that's I. We look at that. So previously we used to have this the chart here. For example, this one is the from Waitakere City Council. So you have a chart here of this it's called the log. This one is log, you know, logarithm. Logarithm on the horizontal and vertical also log, and then you produce a lot of this curve. You know, there's this curve here, and so the bottom part is the concentration time. This concentration time, you can find from the just go back from here, Tc. This one gives us the time of concentration. Okay, the time of concentration. So this one will be different. These different curves, it will be like, you know, the different time, like 2 years, 5 years, 10 years, 20 years, 50 years, 100 years. This means that this once in 2 years, 1 in 5 years, 1 in 100, 1 in 10, 1 in 20, 1 in 50, 1 in 100 years. So the top one you be more severe. You design for bigger storm. For major structure you probably major there's more significant. Probably you have to go for higher, like bigger event, one in 50 years, 1 in 100 years. So this is how we from this curve we can find out what is the rainfall intensity, millimeter per hour. It will range from 1 to this one is 1 at t. So normally you can be the minimum you start time of concentration is 10 minutes, okay, 10 20, okay. So this is how all methods of finding the rainfall intensity. Now we use they got everything is online, digital, and then to find it. You just log at the moment. You just need to log in to the Heinz Niwa, okay, .co.nz, and then you just you can input the easting northing, or you can from here you just click the area. You can zoom it up, and then you click the area. For example, here Auckland, and then some other place, Taranaki or Wellington area, or this Hawke's Bay. You zoom out, click the area. Automatically they'll give you the easting northing. You can put the site name as well, and then you can find what is the rainfall duration frequency, and then that one you which one is let me see. It will give you a chart. Let me see. I just go back. Okay, just go to check the chart. The just now the one, the Heinz Niwa .co.nz. If you go and you click a station, for example this one Auckland. They have many parts. Just then they will give you rainfall, the intensity, duration, rain frequency result. Then they give you what are there's the column here will be the ARI, or the equivalent of the AEP. Once in, like this one is 1 in 10 years, and then the duration, the time of concentration. Is it starting from 10 minutes, 20 minutes, 30 minutes, 60 minutes, 2 hours, 6 hours, 12 hours, 24 hours, 48 hours, 72 hours, and so on. Okay. Okay, just go back. Okay, so the catchment area, I think we have let me see, what is that? Catchment area. Oh, I think I got the wrong link. So the catchment area, it will be, I think it's this one. These are the catchment area. Just go back to that. Okay, so this is the formula. The peak discharge for the Q peak discharge is by CIA over 360. So just now I talked about this time of concentration. So this one you need to find all this value. What are the L? What is the L? What is A? What is S? So in this case, L is the mainstream land, A is the catchment area, S is the mainstream slope. So for example, this catchment all sort of bound by this red line. This is a catchment boundary. So the L mainstream, we need to find the usually the most represented representative stream, usually the longest, you know, so in this case, for example, this one, the longest stream. So usually the most important stream within the system, where, you know, water, you know, usually take the longest time to flow through. So from this one, we can see that we need to find the length of this area, length of this stream. So length of the stream A to B here at this point of point of the what's it, the bridge, the covered crossing or the bridge crossing. So this one is 0.965 for in this example, 0.965 km. And the catchment area, this one, you can, if you do on AutoCAD, you know, you can just click, you make this a polyline, you click, and then the catchment is 0.675 kilometers square. And we from the contour we can read it, you know, this part A is 40 meter. Where you can see, you know, this you have to read the contour. This one 55 here, and then this one probably is some interval of this one is from here, you know, this one is 50 and so on. 50 probably, I'm not sure what you have to check the interval to see. So this one is 40 meter, and B here is 50 meter. So so we can find that you know, the main, we can from we know the land, we know catchment, and then we know the elevations, you know, then we can actually find the slopes. Okay, the slope, that means there's the average land divided by the drop in the slope. Okay, we will see the example later on. Okay, the bottom one is another formula. Okay, but usually we use the Bransby Williams methods to this formula to find. Okay, let's look at the example. Okay, for the peak discharge calculation of a rural catchment. Okay, so in this case, I think we just now we look at that. We got the elevations for A and B, and then we have the land, 0.965 kilometer, and then the catchment area is 0.675 kilometer square. Okay, so we need to find the size of the proposed covered. You know. So the peak flow is this formula, CIA divided by 360. We want to find the time concentration. So we need to find the S, which the slope of the stream. So in that case, you know, 40 minus 15. Just now we said that 40 here and 15 here, and then divide by 0.965, which is the length of the stream. That gives us 25.91, and unit actually is meter per kilometers. So the mainstream slope is meter per kilometer. So the time concentration is FL divided by A 0.1 to power 0.S 0.2. In this case, when we use the area in kilometers square, we use 58.5. So we're going to use the area to be kilometer square, because 0.975. If you want to use hectare, then you have to use 92.7. Okay, so F equal to 58.5. The area is 0.965, and then the area given is 0.675 kilometer square to power 0. And then the S from above here is 25.91. That gives us 30.92 minutes. Okay. So from the rainfall intensity, duration, frequency curve of Mintulu Airport, this in Sarawak in Malaysia. So the rainfall intensity I is equal to 30. We have this 30.92, and then you draw a line up there, and then this for the this curve here actually is for 20 years. Okay, that we designed for the line D. Okay, once in 20 years. So you hit the line D from the draw a vertical line upwards and hit line D once in 20 years, and then we project to the left horizontally. Then we get 160 millimeter per hour. Okay, so using the runoff coefficient of 0.3. Okay, so we that one we look at the this 0.3. We look at the chart, the table. You see the corresponding vegetation, the ground condition, with how much vegetation, then we 0.3. So that will be the, I think 0.3 is the so it will be something like the pasture and scrub covers, grass, the like park, playground, reserve park. Okay, so something 0.3. Railway and seal yards, and so it just sort of it's a it's not very like bushy, but it's of a grass, pasture, scrub cover. Okay, so so the peak discharge, we put everything inside, is give us the Q equal to 9 meter cube per second. So this okay. So I think we'll have a look at the urban area as well. Urban area is still the same formula. Okay, actually the same thing. The urban only thing is the different the the area is a bit different. Area we determine by the boundary of the drain. Because in the urban area you don't have it's a built up area. Usually you have residential or commercial area. So actually is to find the area sort of the area that is sort of they have a stormwater pipe serviced by the stormwater pipe. The area, how big is it? Because usually the water, when they fall on the ground, it will go into the rods. They got the catch pit, or so the catch pit, they go into the stormwater pipe. They usually they have under the rod or beside the rod, they have these stormwater pipes. So all the water in the rod reserve in the area. Even for the water, they'll be from the roof. Usually from the roof, they go down the gutter, and then we go down eventually to the stormwater pipe. So we don't include the water, the grey water, the black water from the kitchen, from the bathroom, from the toilet. Okay, so that one they will go to the sewage pipe. Okay, so the area will be defined by the pipe system, the stormwater pipe system. Okay, where are these let's say the place of interest, where are the upstream pipes, divided by the pipe system. And C is just you just look at the area, how much built up is the area. Usually the urban area will be more built up, like at least 0.5, 0.6, 0.7, 0.8. And the I is slightly different. We in the previously in the rural area, we have this the time of concentration of this formula. But in the urban area, the time of concentration is different. Okay, the time of concentration in the urban setting is calculated from this formula: TC equal TE plus TF. Okay, so minimum is 10 minutes because the chart is only starting from 10. I think the chart here. This one is 10, 20, 30, 40, 50, 60, 70, 80, 100. So 10 minutes. You start from 10 minutes. Okay. So the TE is the time of entry. Okay, the runoff time for overland. Okay, from let's say from the ground, from the roof, and then this one to the point of entry to the open channel. So this usually from the let's say from your roof from the property, from the lot, a subdivision. Yeah, how long it will take to go to the entry point? You know, usually it's a catch pit. Along the road there's a catch pit. The water can go into the stormwater pipe. So just I show this one. So these are the catch pit. You can see that catch pit along. Usually for the roads, they have a lot of catch pit. So the water from the properties, from the lots here, you know, they all go into the catch pit. So how long will it take from the this house properties to go into catch pit? Okay, usually it could be a few minutes. You know, normally it's you know, the water will take, but because this one the all the property, the roof, the house, they got in, they have this the collector pipes, you know, they join straight to the catch pit, you know, from the, let's say from property, from the roof. Okay. And time of TF is a time of network flow. Okay, so this network flow means that, you know, from upstream, from wherever it is, the furthest place, furthest distance, furthest point, how far, you know, you when we calculate the break off point, you know, usually we need to find usually the point of interest usually where we want to build a bridge, where we want to build a culvert, you know. So we also can design for the drain, the size of drain. That means that the TF is the one, you know, there's when we want to do the sizing of the drain, certain point we will need to change the size, then that's how far from, what's the distance from that point to the next point. Okay, the TF. Okay, so the TC is just the TE plus TF. Okay, so yeah. So this one, for example, it could be the TE could be like, these are guidelines here. Either it's 5 minutes or 7 minutes or 10 minutes. Okay, the TE. These are the guidelines. And example, you know, the let's say that you have a line of pipes. The length of the stormwater pipe, let's say is let's say 100 meters. It could be, you know, then you assume the flow, the rate of flow is 2 meters per second. You know, this one you could actually you could have to have some site testing to see how fast the water will flow. Usually the flow rate will be sort of will be controlled by the gradient of the pipes, you know, the stormwater pipe, or some in other cases is the open channel, the slope of the open channel, table drain or the line drain. Then that will give us the TF. So example of using the design if the stormwater pipes. So I got two scenario. One is the stormwater pipe. The other one is the the open drain, the open channel. Okay, so we use a different area. This one is two lots, but for the stormwater pipe, I just use this one. I use one more. 3 lots. So the area A. This is the area. One second area, third area. So we assume that there's in this sub lots we have a drain pass or stormwater pipe serviced by this stormwater pipe OA, and this second lots, so this area B, area A, area C. This area B will be serviced by this stormwater pipe. Also stormwater pipe 1. This stormwater pipe 1 as well. This one is stormwater pipe 1. And this one actually is a collector pipe, you know, from this one. A, B, C, and then go off. Okay, so the area is given 2419 square meter, 2421 square meter, 2464 square meter. And C here is 0.65, 0.65, 0.65. Okay, so the distance is OA is given, O to A is 88, and O to B is 1822, O to C is 156. So that can give us, you know, find the TF. Now we need to find TF. So stormwater pipes, this is actually the outcome, you know, that we have to, after we look through do the calculation, we can get this value. Later on we see that, you know, the stormwater pipe 1, you know, this pipe 1, you know, is 225 mm diameter concrete pipe. Pipe 2 is from here, from B to C. Pipe 2 is we find that is 300 millimeter diameter concrete pipe, and then C, from C onwards, this is stormwater pipe. This is also 300. So we're going to use this formula. So let's say we look at how we can get this answer. Okay, stormwater. This one is residential area 0.65. You know, I think 0.65. This one, the industry, commercial, and shopping areas and townhouse apartment. Things around this. This is a 0.65. Okay, so where else? Yeah, about this. Okay, the this one residential areas 0.45. So this one, the 1.65. Okay, this one just this for this example, I just take 0.65. Okay, so for area A, B, C, we assume the return period ARI to be 1 in 10 years. So T equal TE plus TF, like 7 minutes. Just how we look at the chart, you know, this guideline here, you know, and so this one we get about it's less than 10 minutes, so we adopt 10 minutes because the minimum is the 10 minutes. We cannot have we don't have any value below 10 minutes. So the TC is the bottom one, the bottom value is 10. So therefore, let's say for return period of 10 years, and then for the duration of 10 minutes, look at that. So return period of 1 in 10 years, and then the 10 minutes we get 90 mm per hour. Okay, so we got the three. We put in the value, the QA, QB, QC. So this is the, you know, we use this formula CIA divided by 360. So the C, this is the I, you know, this is 90. A is 2419. You saw just now we raised that 2419. But you know, this A is to be you know, the A is hectares, area of hectares. Okay, area is hectares. What's the hectare is 1 hectare is 10,000 meters square. 1 hectare is 10,000 meters square. So this 2419 meters square, to convert to hectares, you have to divide by 10,000. Okay, and then this one is just a formula 360 at the bottom. So that gave us actually quite a small value, which is 0.039 meters cube per second. Okay, so similarly we do for B. So the area is cumulative. So that means that for QB here, so we just add up the two areas. we just add up two areas. That means that the service by these two pipes. So add up the area. So we just 2421 plus 2419, and then we get a bigger QB. You got a 0.079 meter cube, and QC, the area is the cumulative of these three area A, B, C. Okay, so the others remain the same. You know, the C and then the I remain the same, and then we get a 0.119 meter cube per second. Okay, so for this stormwater pipe, we could calculate it, but it's a bit because the pipe is round, then it's a bit hard to use the by equations to solve it. We could, that one, the to solve it by equation is usually like the regular. If it's a rectangular, then it's easier to find the area of the drain. If it's a round one, it's a bit hard because the water, you know, at different level is a bit hard. So that one you use a chart method, is easier. So this is a chart method. For QA for this 0.039 meter cube per second, isn't it? 0.039. So this one. So we, in this chart here, this one actually based on the Manning's formula equation. Manning's formula. The Manning's formula, I think probably you learn in the fluid mechanics or the hydraulics. I show you Manning's formula is the this is the Manning's formula. Okay, Q equal to 1 over N times A into A divided by P to the power of 2/3 times S to the power half. So we will use this to solve for the open channel, but this chart is derived from the Manning's formula as well. So we have the bottom is a gradient, and the side is a flow, and this side is the flow pipes, and that one is the flow velocity. So we need to, in this case, I just assume a gradient of 150. Okay, so it could be anything. It could be different, depend on the different side. So so we just we have this the flow 0.039. we get a point, we draw a parallel line, just follow the, you know, follow the the orientation of this sort of this alphabet. The 0.04 is is upright, so we draw a horizontal line, and the bottom one is the like gradient. So this is gradient 1 in how many? So put 1 in 50. So vertical line upwards, and then meet this point, and then the line have to follow the curve. There's a two sloppy line. So this curve here, this line is the size of the stormwater pipe. Starting from bottom one is 150 diameter, 225, 305, 35, 381, 38457, 4, and these are the, I think this case is the concrete pipes. So we follow this line through here along the parallel to the top and bottom line, and then we sort of estimate is about 200. Okay, 200. But sort of you know, we choose the bottom, the lower, or the higher. Okay, we normally saw the pipe that we need is 200. So we adopt the 225. Use 225 internal diameter concrete pipe. So if you use 150, you'll be undersized. So the slightly oversized, we use 225. So we don't really go and custom make 200, because you usually use a standard size pipe, you know. So we anything, you know, the in between we use the higher one. Okay, we don't use the undersized pipe. We usually use the one you know, the next bigger size. Okay, so the velocity is 1 here to 1.5, so about 1.3. It's not too excessive. So we have to check the pipe flow, you know, if it's too high, you know, let's say like This one is high, you know, it's 5 or 7. This one is too, the speed is too high, you know. When it come out, the water coming out is, it can damage the acid at the ground, you know. It can cause a lot of erosion. Is the pipe, the zoom oozing out from the pipe is so strong, and it could be actually can damage the pipe as well. It's flowing too fast. So for QA, we get this 225 diameter concrete pipe. The next one is QB. So the QB is you know, this just now we look at that is 0.075. So 0.075, we draw a green line horizontally, and then we still use the 1 in 50 time the gradient, and then we draw a line parallel, this green line parallel to the 2 line, and then we find it's 240. So the next bigger line is we have to use the 300. Okay, the next one, the QC is 0.119. So 0.119, this one, meter cube per second. So we draw a line, the red line, parallel, and then the 1 in 50 line upwards, and then we slope down, and then it's about 280. So 280, the next higher is 300. So we have to use the 300 pipes. Okay, the speed also I think is 1.5, 1.7, something like that. The previous one is 1.5, so it's not too excessive. So we have designed the pipe size, and then this one just to verify, you know, this one, the let's say 119, which is about 120 liter per second, and then you follow the line up, and then the gradient, let's say the minimum is 100. So the green line and the red line meet, and then the blue line you go across, it will give us a 300. The dimension is the dimension of the internal diameter of the pipes that is required. The velocity is about, I can't see. So this one, but this one is the Colebrook White chart. This one mainly used for the water reticulation, to size up the pipes to water regulation. So in this case, I just use it roughly to check, you know, the stormwater pipe itself is it is quite close, you know. Okay, so that's we find the size of the stormwater pipes for these 3 area A, B, C, and then actually there are the 3 pipes here. There are 3 pipes. Pipe 1 for the 3 area coming out from to join this collector pipes, and then the B and C is higher, sorry, the bigger. So this one, this is pipe 1, you know. From this one we use 225, and then for B to C we use 300. Actually B2, and then from this onwards we use 300 as well. Okay, so that's how we size up the stormwater pipe. Okay, so the next one, actually, how we size up the open drain. Let's say instead of stormwater pipe, we use open drain. This is open drain. It could be, you know, if you have a lot of water, a lot of rain, so instead of using the earth drain, you need to use a line drain, I mean, a concrete drain, or reinforced concrete drain. That means that you have steel rebar inside, and then you have this thing pole here. It shows the guide rail. You need to have guide rail on both sides of the drain to prevent people from falling into the drain. This could be quite deep. Okay. So I just make the QA QB. Yeah, just this one just the same as the before. This QA QB, the discharge, you know, just exactly the same. I just make use of the previous one, QA QB 0.039, 0.079. So I just adopt the same QA QB. And in this case, we need to design for the drain 1, open drain 1, and open drain 2. So open drain 1, it will be you know, this one will service the this area, and then the drain 2 will service this two area. Okay, both A and B, area A and area B. So we see how it's. Okay, so the formula here is actually the Manning's formula is Q equal to 1 over N, okay, time A into A divided by P to the power 2/3, and then time S. So the Q is a flow in meter cube per second. N is the Manning's coefficient. A is the cross-section area of the channels in meter square. S is the slope in millimeter per second. Okay, so yeah, so this one, the this video, so I think I can't draw at the moment. Okay, so so I try my best. So the N is the Manning's coefficient. So for the concrete 0.013 says the let's say the concrete surface is 0.013. So this actually is the smoothest. When the surface is very rough, it could go up to 0.0223. The earth is 0.018. If it's a river channel, is very rough, very irregular, very windy, it can go up to 0.3. Some of them is very windy and sluggish and can go up to 0.112. So the concrete drain that I going to adopt, this one is I use the 0.013 for the Manning's coefficient. Okay, so the A is the area of the slope. Okay, so I can S is the slope in millimeter square. So the slope, let's say assume the slope is 1 in 300. Okay, for the slope here. So the S is 1 divided by 300. In fraction is 0.033. Okay, the slope, the width of the drain is 0.25, and the depth of water is D. So the area is 0.25 D. Okay, sorry, I don't have a diagram. Actually, if in class I can draw in a diagram on the whiteboard. Okay, the P is the wetted perimeter. P equals 0.25 plus 2D. Okay, 0.25 plus 2D. So the wetted perimeter. So from table, okay, for this concrete channel, okay. So I try to get to show what is the area and the wet perimeter, but so far I think it's a bit hard for me to do at the moment. So I will draw a figure. I think later on there will be some tutorial. I will show what is mean on the diagram, how to get this this one area. Area usually is like so the width of the drain, multiplied by depth of water, like 0.25 D, and the wetted perimeter just the bottom plus the two sides of the drain until the water level. So I think later on, there's a chance I will show it on the diagram. Okay. Okay. From a table, n equals 0.013. So that gave us the Q. For this open drainage design, actually same as the stormwater pipe. The Q, which the Manning's discharge, we have two Q. Q is the peak discharge. Q equals CIA divided by 360. That is the peak discharge. This one the Q for the Manning, from the Manning equation. This the Manning discharge. So this Manning discharge need to be at least equal or bigger than the peak discharge. So if it is smaller, then the stormwater pipes or the open channel will be too you'll be undersized, under design. The things will be so the capacity will be smaller. If it's a covered, you design covered or bridge area, the whole thing can be, if it's under design, the whole thing can be damaged, can be destroyed, can be washed away even. So this one, the things that we use a try and error methods, make sure that the QM, the Q of manual discharge, is bigger than the Q, the peak discharge QP. So we look at these two areas. Okay, from this we put in the formula for this one, the AP. We got the expression in terms of D. A is called 0.25 D, and P is 0.25 plus 2D. We substitute inside. We know the slope. I think the slope here is I think is 0.033. So we just get an expression in term with one unknown, with one variable is D. So we don't simplify. You just put in this general expression. So we try D equal to, that means the width of the drain is 0.25. The width of drain is 0.25. We said that the width of drain is 0.25. So we try depth is called 0.15 D. Okay, we just have a try. So we put into this formula here, into this expression, equal to 0.027. 0.027 for the depth of 0.15, and we need the for the QA 0.039. So this one is not sufficient. So we try second try 0.25 the depth, and then put into expression, and then it's 0.052, which is greater than 0.039. So it's okay. So assume a free board. Free board, that means that we allow a gap. The water, we don't allow the water to go to the top of the channel. So we have so the water will be below the top of the channel, like in this case 0.1 meter. So that's a free board. Just now we talked about the free board for the bridge and for the cover as well. So the size of the open drain is just now, actually it's a 0.25, isn't it? 0.25 is 250 mm, and then we got 0.25 depth. So the height will be plus 0.1, the freeboard, so it becomes 350 mm high. We repeat the same thing for area B, which is this one. So now the the area will be more. Sorry, we don't have to, because the expression we just said, we show that that we know that we need to satisfy this the Q 0.079. Okay, so so we put this expression, we try 0.35. Okay, the depth. Okay, we still maintain the same width. The same width is 0.025. So we put in this expression 0.078. It's approximately equal to 0.079. So okay, so we said that okay, we can use the because we still have allowed a free board as well, 0.1. So we say that for this drain B, this one B from open drain B 2. So we the size is 250.25 meter, so become 250 is 250 mm, and this one 0.35 plus 0.1 is 450 millimeter high. Okay, so that's it. Okay, so that's all for the part 1 of this rotting drainage. Okay, so I think we'll stop here. Thank you very much.